All right, I'll start with some remindings and I guess today will be about variational approach. Okay, so what variational approach allows us to do is to solve time-independent Schrödinger equation. Okay, and this is a great equation to solve, because then it will give you convenient basis for presenting, say, your initial function as linear combination, right? And then you can easily obtain the dynamics by just adding the these imaginary exponents, right? So if you know these guys, then, and you're given some initial conditions, right, these coefficients, that, well, it doesn't really matter whether you are given the psi in the coordinate representation or psi in terms of this linear expansion, you still can do it, right? Or you go from one to another by getting the coefficients as integrals of psi x 0, right? So at any rate, your initial conditions must be given so that you can obtain the wave function at a later time. Okay? If you don't have this guy, then you cannot solve time-dependent Schrödinger equation. It's a first-order differential equation in time, and so you need to have initial conditions. You need to have your start. Okay? And then you can move on and solve the time-dependent Schrödinger equation. And in this course, we will also consider the case when, say, in spectroscopy, technically your Hamiltonian becomes time-dependent, and you cannot use time-independent Schrödinger equation, but there is a perturbation theory that allows you to essentially transfer everything back to time-independent Schrödinger equation for the part of the Hamiltonian that doesn't depend on time. That will be covered later. Today we will focus, I guess, initially on how to solve this problem if it's not amenable to analytical solution, if it's not a model problem, like particle in a box, harmonic oscillator, that sort of stuff. Then variational approach is one of the ways to solve this problem. It's approximate approach, so you usually is using some form of the wave function, and it usually depends on some parameters you put in your trial wave function. The simplest, I guess, simple example would be that this trial function of yours is a linear combination of some known functions, which are not necessarily eigenfunctions of the Hamiltonian, because if you knew eigenfunctions of the Hamiltonian, you wouldn't be solving, or you wouldn't put the coefficients for solving this problem, right? So that's the simplest example, but in general, it can be highly nonlinear, right? So variational approach will allow us to actually use both linear and nonlinear constructions. So one of the examples of nonlinear construction, imagine you could have just a kind of, for a simple particle in the box problem with a bottom that is not flat but rather corrugated somehow, what you potentially can use is a trial wave function of the form x into the power of alpha, and multiply by x minus L to the power of beta, right? And this will be phi of x with parameters beta and alpha, okay? So why do I use this form? Because this form respects boundary conditions, right? So it's a particle in a box with slightly modified box bottom, right? And so we know the solution must be 0 at the 0 and at point L, because that's where boundary conditions are. Okay, so this is an example where you can have parameters in not linear form but non-linear form. Okay, so some power phi alpha x and times phi beta x. Okay, so now a variational approach starts with variational theorem. Do you know that statement? That variational theorem makes, and it is that if you have some trial function phi, and you're making this product and divided by phi, because function might not be normalized, so this will always be larger or equal than the lowest eigenvalue of our time-independent Schrödinger equation. Just to avoid writing lowest all the time, let's just accept the convention that my E1 will be the lowest, and then E2, E3, and so on will be other eigenvalues for the time-independent Schrödinger equation. Okay.
What we're talking about here with the energy being the lowest value, are we doing this variational approach because the Hamilton is telling me that the potential is a function of time? Or
well, we're not doing a variational approach right now because I'm kind of motivating variational approach. First formulating variational theorem. Okay. So we will be doing this. We will be looking for the way to find the best approximation in the form where the function, our trial function, will depend on our space variables and some parameters. They can be linear or nonlinear, right? And so the variational approach will tell us how to find these coefficients. Okay? And before we get to that, I would like to first state that there is this variational theorem that is this statement. Okay? And that will help us to figure out how to find these coefficients, or alpha and beta nonlinear coefficients. How do we approach this problem? Okay? And it all kind of starts here in this statement. Okay, because what this statement kind of may push you toward is that if you have some parameters in your trial function phi, then if you know that this value always larger or equal to the lowest energy, then in order to improve the estimate of phi, you need to minimize this expression with respect to parameters, right? If you are looking for, say, phi that will take place of phi1, the ground eigenfunction. Okay? So for that, we start with the variational theorem that is formulated here, right? So have you ever seen this statement before? So should I skip the proof? No? Okay. Good. All right. So I like the proof because it kind of emphasizes the power of imagination. Okay. So now let's imagine we have these states. All right. We don't have them, but let's imagine we have them. All right. Then, since they form complete set, we can expand our function as linear combination of these functions, which are eigenfunctions. Okay? And these coefficients well, they're different from these coefficients, of course. So they're coefficients of expansion of our trial function in this hypothetical, which we imagine to have eigenfunctions of the Hamiltonian. Okay? All right. Okay, so we have this expansion. Now we can form this expression. There will be two parts, phi h phi, and the denominator, right? So phi h phi, we put this linear combination in bra and ket part, right? What it will be is linear combination of n m cn star cm, then phi n h phi m. Do I need to comment this step? Or it's obvious? Okay. Just be careful whenever you put the sums, and there are two sums, and they go in product, then you should, for the proper bookkeeping, have different indices. Otherwise, you will be missing some of the cross terms. And if you're hesitant about the correctness of stuff you're doing, you can just always test whatever you generate on the example of, say, sum. Substitute the abstract sum by just a combination of 1 and 2, right? C1, phi 1 plus C2, phi 2, instead of some one part, another part, how many terms do you get? And then do the abstract derivation and see how many terms you get if you do this transition to the concrete sum at the end, right? So that allows you to test that you didn't make any mistake along the way. All right, so this is the result. And now, since we stated from the beginning that phi m and phi n's, they are eigenfunctions of h, right? So then this becomes simply em, right, multiplied by phi n phi m, right? And
sorry, so phi sub m, we just suppose we know the eigenfunctions, okay? But then what is the phi with no subscript that we're?
This is our trial function.
The trial function. Okay.
Yeah, we're proving this statement where you give me a function,
yes,
and I put it into this expression for the Hamiltonian we are considering, and I always bet on no matter what function you give me, the result will be always higher than the true eigenvalue, or the same. Okay? It cannot be lower.
Okay.
It cannot be lower, yeah. So if you bet money on this thing being lower, then you will lose all the time. I can play this game all day around. Okay, so now what do we have here? These guys, they are orthonormal, right? So then this becomes delta Kronecker by definition of what orthonormal functions are. And then, since this is delta Kronecker, the only terms that are non-zero in this sum where m and n are the same. So this becomes a single sum, say, with respect to n, and then we have Cn squared. The step here is that this m becomes n, and Cn star Cn becomes Cn absolute square, and then E also becomes En only because m must be equal to n. Okay, and this now gives 1 in the diagonal case, and off diagonal 0. Right, so this is what we got. Now let's consider the second component, phi, right? Here the situation is even simpler. There is no Hamiltonian, so what we get, again, double sum initially, Cn star, Cm, phi n, phi m, right? And then this is delta Kronecker. This becomes just a sum Cn squares, right? Now I can write down that, say, for brevity, let's say this is my E tilde. So the E tilde will be equal to the ratio between Cn squared En and Cn squared, right? And now I claim that this is always larger or equal than the following ratio. Is it obvious? Why can I claim that?
Why do we still keep the sums for the coefficients?
Why not?
Because over here we just have the lowest energy, and that's what we're trying to show. But over at the end of the board, we've got the lowest energy times that sum divided by that whole sum.
Mm-hmm. Yeah, well, here the transition is that I substituted all the ENs by the lowest, okay? By 1, which is the lowest, right? That's why I can write that this part is always higher or equal than this part.
If the energies are always decreasing.
No, they do not increase, mathematically speaking. This condition is not the condition that energy are increasing. This is a condition that energy are not decreasing. Mathematically, there is a difference between non-increasing and decreasing, right? So these guys, they are non-decreasing. But there is a possibility that they are all equal, right?
Yeah.
So that's why they are non-decreasing.
Okay.
Okay?
So E1 is either equal to some other one or less?
Or less,
Okay.
yeah.
Okay.
That's right. That's why this term is always higher or equal than this term, right? And now, I guess that's what you are suggesting, is we can get rid of the sums because we can take E1 out of the summation since it's not participating, right? And then this becomes E1 since these terms are canceling each other. Okay? So this is the proof that whenever you have a trial function, then you will be getting the energy that is always higher or equal than the lowest energy of the problem, right? So that's the variational theorem, easy to prove.
And for any Hamiltonian, are the energies always non-increasing?
That's a good question. So there are some conditions here, and they are mostly related to the fact that you are representing your trial function as linear combination of eigenfunctions of the Hamiltonian, right? So imagine the case when these functions are all even functions, or all odd functions. And your trial function is, say, the opposite, right? So if these guys are even and your functions is odd. Okay, say these functions are 1 x, well, let's forget about 1 x, x cubed, x to the 5th power, and so on, odd powers, right? And this guy, you decided to work with x squared, right? So then, there's no way you represent x squared with these functions, okay? So then, this whole thing will not work out, okay? And this is important case, well, because if, say, you're working with electrons are fermions, and we'll talk about this later, but essentially the two-electron function, x1 and x2, there's a condition that this function must be equal to minus the function where you permute the variables, right? So that's the relation. The Pauli's exclusion principle. It all comes from the fact that the particles are indistinguishable, then the psi square for the object which where you say, okay, this is my first particle and this is my second particle, this must be indistinguishable from the situation where you name your particle that you named first before as a second particle, right? So then for this quantity, it shouldn't matter. But there are two solutions for this equation. Well, actually, there are many solutions, but two solutions for which are making the most sense are the ones that are fermions, right? And bosons are the ones that have x1, x2 equal to x2, x1, right?
That statement that you underlined, what?
This is the condition of indistinguishability of particles. Elementary.
One of them you have the x1, x2 inside it?
Yeah. What I meant was this.
Oh, okay.
Yeah. Right, so, because what we measure, like a physical observable, is of course the probability density, not the function itself. That's why there is ambiguity in the function. Okay? And so those are bosons, and then can you tell me what are the other solutions for this equation?
Any complex number with a magnitude of 1?
That's right, yeah.
But we throw away all the complex values.
They are called anyons, I believe. Anyons. Not fermions, not bosons, but anyons. Yeah, well, physicists are still looking. I'm not familiar with research in that area, but well, potentially it's in a solution, right? With, as you said, instead of -1 or +1, you have exponent of I phi, the phase, right? But then you need to find real particles that satisfy this condition, and I'm not sure they found yet. All right. Okay, so those are fermions. Why am I talking about this? I'm talking about this because if you are working with fermions and you all of a sudden decided to present your function, your trial function for the fermionic system, as I'll say, since it's a kind of function with two variables, one way to present it would be x1, x2 equals to phi x1, say I, j, x2, right? And then you sum over ij. So in the chemistry language, this is sometimes called kind of atomic orbitals, right? And they correspond to the, or even molecular orbitals, doesn't really matter. But this is a single particle functions. And then to form multi-particle object, right? So you need to have products of them. Now, if you're working with fermions, this is wrong, simply because with this function, you don't have this condition satisfied necessarily. Okay? So if you put some Cij coefficients, then you may find it useful to have Cij equal to minus C Gi, something like this, right? So this is an anti-symmetric condition that for the, again, to avoid the abstract language, if we do phi 1, phi 2, right, then there should be a term where we go phi 2 for x1. This is x2, phi 1, x2, right? So if we have this term, we need to have this term.
For multi-component systems, one way of attacking that is just use the state determinant.
That's right. This is a determinant for the so-called Slater determinant for case of 2 by 2, where you have phi 1, x1, phi 2, x1, and then phi 1, x2, phi 2, x2. And I'm forming the determinant of this matrix of functions. So then this is the result, right? Now, if I start building, just out of curiosity, start building variational ansatz, or variational construction where I do not impose necessarily this condition, right? So that there's, if we have 1, 2 component, then there is always should be 2, 1, right? If I start with the function which is phi 1x, phi 2x, and just, well, put some arbitrary coefficients, or if it's a one product, just like that. So then, that's what I think Fock found when he was deriving the Hartree-Fock method, right? Then you will get the wrong solution, and it can be lower than the true solution, because essentially you are trying to represent one type of the symmetry, which, well, these products, they are not symmetric or antisymmetric, right? With well, for the problem where you need to have antisymmetry in the wave function, all right? So all your eigenfunctions in this expansion, they are antisymmetric if you're solving problem for the fermionic case, right? But your trial function, if you take it of their own symmetry, then you can easily go below the lowest energy, okay? Simply because you kind of violating, you're going outside of the space, physical space of the Hamiltonian. So it's not commonly emphasized, but operator is usually, well, needs to be taken as the definition of operator also should include the definition of the space where it works, right? If you have one, say, Hamiltonian for the helium atom, right? So it has certain components, but that's not full definition of what Hamiltonian is. You also need to specify, if you're working for the solving an electronic problem, that the space of functions where this Hamiltonian is working is antisymmetric those antisymmetric functions, right? But if you substitute the space of antisymmetric functions by a space of symmetric functions, then it will be technically different Hamiltonian, and the solution of time-independent Schrödinger equation for that Hamiltonian will be different. Okay, so that's one thing where you need to be careful. All right, now this is all great, and you now know how to, well, no matter what construction you have, how to obtain approximations to the ground state, right? All you need is you have now this E tilde, and in the case of, like say, simplest case would be you would have, say, two functions, phi 1 and phi 2, for your trial function. We're still talking now about one particular spatial variable, right? And so the simplest application would be C1 phi 1 x, where this is some kind of function, and then C2 phi 2. If you like me to be concrete, one problem you can think of is inclined bottom particle in the box. These guys are eigenfunctions of a normal particle in the box problem, and you're trying to find the ground state of this particle in the box problem. Okay, so then you have these two variables. Well, initially they are parameters, now they are variables to play with, because we can construct this E tilde. It will be C1, C2 function, and how do we find the minimum of that function? Everyone taken multivariable calculus, right? I presume. So what do? We take derivatives, right? And we assign them to 0. This gives us two equations, two unknown variables. So we can obtain C1, C2 from these equations. And we'll have solution, say, C1 vector.
And the E tilde is that quotient?
E tilde is this guy. Not the true energy, but rather this approximate energy that we obtain from the expression I wrote, right? With the trial, the difference is that you don't have true wave function to put here. But if you put the true eigenfunction, then it will be exact, yeah. Okay? All right, so there are two solutions. C2, C2. One will correspond to the minimum of energy. Another will correspond to, well, extremum, essentially, because this is not the condition for the minimum, right? This is a necessary condition for the minimum, but not sufficient. Okay, do you understand the difference between necessary and sufficient? Yeah. So, good. So this can give us also, what? Maximum and also saddle points, all right? That's actually a good part about the variational principle, or, well, essentially this system of equations, because they are not only giving us the ground state energy and eigenfunction, but because there are two solutions, they are also giving us the second solution of the problem. Or no, if we are approximating some Hamiltonian that contains potentially infinite number of eigenstates, like this one, right? Then we're getting approximation for the first excited state, okay, by doing this. And if we add more components, then we'll get 3 solutions, 4, 5, and so on and so forth.
And that phi sub 1, phi sub 2, and phi sub 3, those are just any eigenfunctions for, like in this case, the flat Bach particle in a box, like the Hamiltonian for a flat box? Or
That's right.
What is phi sub 1, 2, 3, I guess, my question?
They are particle in the box problem solution, right?
So do they have to be the first 3, or could they be any?
They could be anything.
Any of those?
But it would make sense to take, if you are interested in the low, now we're kind of leaving the domain of science and go into the domain of art, right? So there is certain intuition you want to put, because it's essentially the problem here is that you don't want to have many coefficients to adjust. You want to capture the truth with the smallest or with the most economical ansatz or construction. Because the more coefficients you have, well, the bigger the system of equations, and if they are not linear, then it becomes horrible mess. But generally, the idea here is that if you are interested in low energy physics, and say you are interested in ground and first excited state, then you would put probably the states which correspond to problem that is closest, but you can solve, right?
Okay.
And there is some rationale from the perturbation theory point of view, but I'm not going to go there right now. It's still for more complex problems where the problems that you can solve, they are still too far from the problem you're interested in, then it becomes kind of hard to find the good functions or good approximations for the functions you are looking for, right? But this goes beyond, of course. It requires some physical intuition, essentially. Anyway, so the point I want to make here is that, yes, we can obtain the minimum solving this, but on top of the minimum solution, we also have something else. And that should prompt you thinking, okay, now can we use the variational approach, or essentially making some construction for a wave function, and then finding the extremum points, okay, of this to solve the time-independent Schrödinger equation, okay? Because what I'm saying from this example is that we can go beyond this approximation where we're looking for only minimal or the ground state wave function, right? So it looks like, in linear case, you obtain a system of equations that generate more than one solution, for sure, and then can't we just go, well, further and further, adding more states? Will what we get be equivalent to solving this problem? Okay? That's a non-trivial question, because we for sure know that the minimal solution would correspond to the ground state. But why are we so sure that the other solutions will not be just something spurious. Okay? And there is a mathematical way to show that, in general, variation of this so-called functional. Now, why is this a functional? Because this E tilde construction can be thought as something where you put, in my thought experiment with betting on whether it's lower or higher, like Taylor was giving me a function. So now it's not me, but E tilde that is accepting a function, right? And what it produces is a constant, well, also E tilde, right? I put it as E tilde. But really it's a functional that is accepting a function and giving you a number. Okay? And now the question is, if we formulate a problem that we are finding extremum of this functional with respect to function, will this problem be equivalent to original H phi equals E phi problem? The answer is, of course, yes. That's why it's useful, and that's why it's mathematically rigorous to search for the solution of time-independent equation as a extremum of the functional. Why is this important? Why this is going to be useful? It turns out, since if we're working with the real systems, then it's always about how to make better approximations. Turns out finding approximations for this problem is more straightforward than finding approximation for this original problem. Or you can think of this as one way to go to approximations, because clearly you can parameterize your function in a different way, and you put in the functional and then you vary the functional. Now I'm using this variation word. What I mean is that when your function is just represented as linear combination with a few parameters, then this is nothing but multivariable function, right? Because these are numbers, and you are finding the extremum. Okay? But in order to prove that equivalence, what I wanted to show you, that's why I announced that today you will learn how to differentiate in infinite dimensional space. Technically, to prove that, we need to go and well, find some equivalence of the derivative with respect to function, right? So we would like to write something like this for the functional, right? Where this derivative, well, it's not that simple, because what we would like to do to find the extremum is to find the to vary the functional with respect to a function. And function, it's not one particular value, right? So if you have a function, say phi 0, then the variation of that phi 0 plus some function, I will denote it as delta phi, right, can be different from phi 0 in all points, right? And so what we want is that we want to find phi 0 for the minimum condition, for example. If we have some addition of arbitrary delta phi, right, this value will be higher or equal than the value of phi 0, right?
Is this just like the action?
It's like an action, yeah. It's exactly like an action. More than that, there is a way to connect everything to the action principle, essentially. So what Tyler means, like, I don't know whether the graduate students, you guys studied this classical mechanics at the level of Lagrangian formalism and Hamilton formalism. Well, mostly Lagrangian formalism. That's where the action starts. So the classical mechanics, the way you probably know it, is Newton equations, right? But there is another way, more convenient for problems with constraints. Constraints means that, well, particles are moving on some surfaces which are determined, right, with some kind of potential functions, right? So then the way you can obtain the same Newton equations is for formulating the so-called action, where which is the integral of Lagrangian function. Lagrangian function has positions and velocities and time in it. I guess it's a different time. Right? And the Lagrangian function is defined as the kinetic energy minus potential energy. Okay? Now, if you set up your initial conditions that your particle moves from essentially some time 0 to time t, right? There are various trajectories it can take. So the classical trajectory corresponds to minimization of this functional again, because it's functional because what it takes, these functions of position as a function of time and the velocity as a function of time. Okay, so this Lagrangian function, it is a function. What makes this whole thing functional is that you're integrating. Okay, so then you are getting at the end a number, right? Because you're integrating over time. And so the classical mechanics, Newton equations, they can be obtained from a condition that this functional, the first derivative, this construction will be actually defined with this delta symbol. This first derivative is 0. Okay, and then you obtain all these Newton equations. All right. So in our case, the functional is this. It's a quantum case, so we have a different functional. More than that, why is this whole thing is very useful? Makes me excited because you actually can formulate the functional also for time-dependent Schrödinger equation. Okay, so you can solve by doing some kind of ansatz for the time-dependent wave function. Essentially solve this equation not as a differential equation, but as a minimization problem for a functional. Yeah.
And this E tilde, does that have a name?
E tilde.
If I wanted to look at more information on it, what would I?
You would look at the variational calculus. Okay, so, and I will try to stress the analogy here with multivariable calculus. Yeah, multivariable calculus. Not variational calculus is a calculus when you go to the infinite dimensions, because at every point which are infinite number, even in one dimension, you can change the function, right? Yeah. Because you add into a function another function, which is changing the original one. Right? That's why it can be thought as taking the derivative of the, not the infinite order, but an infinite number of points. Yes. Okay? So it's an extension of multivariable calculus to infinite dimensions.
Yeah, I'm mildly comfortable with calculus and variations. I mean, that might even be an overstatement. But I mean, like E tilde, like this would be something that we could use to find the energy for a weird potential. Like something.
That's right.
But I mean, like I got this cool book. Like if I wanted to look that up in here.
There is a, I'll direct you. There is a chapter on time-dependent variational principle, but I guess to my taste, none of the books actually covers things perfectly. So in this book, there is no like a unified chapter on variational approximation or variational approach to quantum mechanics. It's separated. This book has its own angle, right? So Tanner, he emphasizes the importance of time-dependent approach that you can obtain from time-dependent Schrödinger equation even without solving time-independent. All the characteristics. That's why it's more fundamental. I agree that it's more fundamental because, well, my simple argument would be that even, well, in the cases where this cannot be written, this still can, be written, right? So it's pretty simple. But he goes beyond that. He, of course, goes into the details and shows that you actually can get these quantities for the situations where this can be written, say, right? So then if you completely want to avoid solving this problem and your focus is only this problem, can you obtain, say, energies and the functions just by doing this?
And you use this method here?
Well, essentially, to make long story short, what you can do, the simple answer, I don't know how simple though it is. So you need to take autocorrelation function of this function you obtain and Fourier transform it. Then what you're going to get is eigenspectrum of your problem. Okay?
Okay.
So what you're going to get as a Fourier transformation of this guy, function of omega, you'll get peaks at the values of eigenenergies. And that can be easily actually shown because you just use this. Okay, once you ask that, I'll show. Okay, so what do we have? We have, again, use the power of imagination and imagine that phi n's, the eigenfunctions of time-independent Schrödinger equation, they are given to us. Okay. They won't be needed at the end, but yeah, they will go away. But just to make things simpler, we will form the autocorrelation function that will require us to. Autocorrelation function is usually a function that averages some characteristic for 0 time and later time. Okay, so what we will be doing is taking the scalar product of psi t, and I don't write x because x is kind of an internal variable where I'm integrating, right? So this is autocorrelation function because there is a property overlap which I have as a function of time, right? So 0 and function time. Okay, now this thing will be Cn phi n's, right? And then at later time, this will be Cn phi n exponent t divided by h bar, right? Now let's take this again because of the orthogonality. What we're gonna get is one sum will go away, so there will be Cn squared, right? And then will be exponent of minus I Ent divided by h bar, right? So this function has a time dependence for this. And then if you take the Fourier transformation of time from 0 to infinity, or technically from minus infinity to plus infinity, of this guy, phi 0 psi t, then with the exponent, of course, I omega t, right? Then it's a sum over n, Cn squared, and then the integral of omega minus En h bar t, right? Yeah. And so this integral is just a representation of a delta function, right? Yes. It's a delta function at omega minus En divided by h bar, right? So we have collection of collection of delta functions multiplied by the constants. So, and that's when you know this object from minus infinity to plus infinity. Oh, I guess it shouldn't be minus infinity because you start with 0, right? And then it will be like a half of the delta function. All right, so that doesn't matter so much. From this picture, what you get is the spikes at the if you plot this object, and here will be some finite time t, but this will be, instead of an infinite delta function, will be some Gaussian, essentially.
Okay.
Right? Because the whole idea is the same, right? So it's not up to infinity. So if you plot what, like your omega versus this object for a particular omega, then you get Gaussians that are centered at the points of the eigenstates, right? And so nowhere here, actually, I need these phi n's, really. To obtain this quantity, all I need is to, if I have this object, not even expanded, but just this object, right? I need to know how to so-called propagate or obtain what the object at the later time will be. And for that, I don't need to use this expansion. There are other methods, like time-dependent variational principle is one of them. Essentially, you do not represent your function as an exact linear combination of eigenfunctions of time-independent. You represent it somehow differently, right? All you care is that there will be time dependence there. And that time dependence then later can be transformed through this expression into something that will have spikes at the E energies, right? That's why, well, one of the reasons standard like time-dependent approach. Solving this problem sometimes very difficult, okay, and unnecessary, really. Okay, back to variational calculus. So how do we do variational calculus? Again, different books present it differently. My whole kind of philosophy is to keep it simple, right? And I think math can be made very difficult by essentially doing it in a very abstract way. But I think everything would be so much easier if people cared about connecting what you know from the previous chapters. Like, say, if you're doing infinite dimension calculus, it must be somehow connectable, at least maybe not on the rigorous mathematical level, but at least on the kind of making sense level with the material from multivariable calculus, where you're operating with a finite number of dimensions. So, in the multivariable calculus, what we have is, various derivatives, right? So there's partial derivatives. That's one quantity that it's really hard to forget because it's kind of coming as a generalization of what's happening in a single variable calculus, right? So if you have x and y variables, right? So then there is a partial derivative. And you all know that, right? So we just used it for the consideration. Do we need to make a break? Or?
I just need I drink a lot of coffee.
Okay, well, let's make a break.
Vector is that same linear function of the eigenvalue.
Yeah, there is just a typo in this problem. It must be linear operator, not the function.
No. So where?
Yeah, here. Come on.
I know exactly what you're talking about.
And I thought that I can do it in terms of matrices. Basically, it's saying, so there's some operator. You have the eigenvector, and you know that its eigenvalue is this. So then it says, show that some linear function of your operator acting on your eigenvector is that same linear function on lambda acting on that vector. And then at first I was like, oh, that's fine. In terms of matrices, that's just going to be like, say, B, A plus some scalar A. And I was like, wait a second, but we're not talking about matrices. We're talking about operators in general. So I was just like, what does it mean by linear
function?
Yeah, like what form can I have there?
Okay, so general definition of what linear function or map or operator is, right? It's if you have objects which are vector objects or operator objects, you can multiply them by constants, right?
Yeah.
And you can sum them usually. So linear function means just that you can take a function of the operator, take a function, and then multiply by alpha, right?
You can pull out scalars if you break it.
But then later I realized it's probably just a typo in the formulation of the problem. What he meant was that the function can be nonlinear, like exponential function. But
because then that's exactly
okay, just wait a little. Okay, so function can be nonlinear. What he meant by linear was the operator. Operator is linear, but function can be nonlinear. You still can show that this is true for a general function. Function just needs to be analytical. So and the key, the hint for you is that you just do the Taylor series expansion, and you can represent the diagonal lambda I kind of diagonal operator or diagonal form of the matrix as U dagger, right? And so then you notice that f of x can be expanded in a Taylor series, right? F of x0 plus blah, blah, right? So then using that and that, you only need to know how to do the powers of A.
Which we proved earlier.
Yeah, and then you can combine back to the function of the diagonal. So essentially, function of diagonal matrix is easy to take, right? So it's going to be just a function of diagonal elements. Function.
Wait, so lambda, we're saying that equal. I thought lambda was the eigenvalue.
That's right.
So how is it equal to that product of three matrices? Because isn't that going to give you the?
This is this is already a matrix that is obtained after you diagonalize.
Lambda times the identity. Okay.
Well, it's kind of a matrix on its own, because when you diagonalize with U as a matrix, you're not getting one lambda, you're getting the whole matrix with different lambdas. Okay. When you solve for eigenvalue problem, you put in the form that A minus lambda identity, right? Determinant equals 0. There, it's a single lambda. But when you diagonalize or go into the basis of eigenfunctions or eigenvectors, you're getting the diagonal matrix with different lambdas on the diagonal. Anyway, talk to graduate students. They already explored this problem. I can give you hints. All right. Yeah, that mistaken tenor I wasn't aware of. So. Okay, back to derivatives. Now, when we have one variable, it's all simple, right? When we have more than one variable, there are possibilities. So the simplest one is so-called partial derivative, where you change one variable, right? Say this is a partial derivative with respect to x. You change one variable inside of the function of two variables, x and y, and you take in this ratio. Okay, and then you take in the limit of delta x goes to 0. Okay. Then there is this gradient operation, right, that makes a vector out of the two derivatives. That's another possibility, because now you can have partial derivative with respect to x, partial derivative with respect to y. Okay. Also, there is so-called directional derivative that will be very, very important for our variational approach. What directional derivative does is essentially, if you have a function, say paraboloid, that's our function f, right? And it's x squared plus y squared. And let's make it alpha, beta, some coefficients, right? So then there is x, y. And this paraboloid, since the coefficients alpha and beta are different, so it's squeezed. It's not if you cut it horizontally, it's not going to be a circle, it's going to be ellipsoid, right? Because the function f grows faster if you increase x than if you increase y, say, right? If for alpha larger than beta, that means the function grows faster when you increase in x by say one step than when you increase in y. Okay, and so then partial derivatives, of course, will be different for x and y, but then also you have an option to take a step along any arbitrary vector, right? So to define the direction, we usually use vectors Can you see here?
Yeah.
Yeah. So usually we use vectors of the unit length, right? Kind of makes sense, direction, unit length vectors. And then we can modify partial derivative by doing this according to the split of if the epsilon is a vector, then if 90% of epsilon goes along the x direction, then epsilon x will be 0.9, epsilon y will be 0.1, right? And then the t is a scaling parameter, right? Just since the direction is already set up by epsilon, now we can vary t, and this will be the definition of our directional derivative. Okay, so that's how fast function grows along the particular direction epsilon, right? Now you can see that with the functional and with functions, you can take similar approach where you just need to extend this directionality for the function. Essentially, directionality will be this function that modifies our original function. And it will be like an infinite vector because at every point, every point means it's a new direction. Potentially, we can modify our original function along this, well, along the direction which corresponds to this point in a certain way. Say, this point means more than this point, or this point, for example, where in this point, because the delta f is very small, right? So it doesn't modify phi 0 much. Okay. So the way to generalize then would be if you have a functional e tilde, right, and then the variation of e tilde that will depend on psi and delta psi. Okay, like in the case of directional derivative, there is always dependence on the direction. So we cannot avoid dependence on direction because depending on direction, the derivative will be different. Here, we cannot avoid dependence on the way we vary functional, right? But the limit that we write is very similar to directional derivative. We use, again, t as a scaling parameter, and then we will take a difference between e psi plus t times delta psi minus e psi okay. So for finite t, this is just a new function, right? Psi, new function equals to psi plus t multiplied by delta psi, right? And this function, say the norm of this function, we can make it 1, okay? Then it really becomes, you can even write t goes to, you can even write something like the norm of t nabla psi goes to 0 because of the t, and then you have a limit of e psi plus t psi minus divided by t psi norm. You can think this way as well. But for practical calculations, the easiest way to think about this is the following. It's a derivative with respect to t for the functional where we have psi plus t delta psi at the point where t equals to 0. Right? So this definition makes it really simple to take this variation, because all we need, we formulate our function now, we put instead of psi this construction psi plus t, which is some variable, that's just a one-dimensional variable, times some new function delta psi, which we do not specify. It's just some function that sets up the direction along which we vary, right? Then we take the derivative of this construction as a function of t. That is just a taking a derivative, like essentially that's a taking of derivative of a function, right? Because with respect to t, the functional is a function. I will illustrate it in an example. So this is just a normal differentiation. And then we are considering, after we differentiate it, we're considering that the t should be equal to 0. Okay? And so this, if you want to kind of investigate this topic further, this is called Gateau derivative. Sorry, this is Gateau differential, or weak differential. It's written this way. Okay, and if you want...
That means cake in French. Cake derivative.
Cake? Okay. All right, so, or weak differential. The second alternative name can prompt you to think, is there a strong differential? There is a strong differential. It's called Frechet differentiation. Frechet. And it's defined as more along the lines of a differential in the multivariable calculus. So if you are familiar with multivariable calculus enough, then you may remember that existence of partial derivatives do not guarantee existence of differential. Okay, because what differential means is it's the df over dxi, right? So sum over all variables. And actually, there are some conditions that requires this to be a linear map. So I don't want to go too much into this because that's kind of a tangential point. For physics, usually weak and strong, they will be the same, okay? Because in physics, the general idea is that everything interacts with everything, and you don't have sharp boundaries in the, well, very sharp boundaries, okay? So everything is smoother than in this abstract math, right? And in math, people consider some weird examples where, say, you have all the partial derivatives, but you cannot formulate differential, right? And the functions which they operate with, they are really outside of the physical domain, okay? So that's why it's not very interesting. At any rate, so let's just then see how this Gateau derivative or differential, how do we work with it. And one thing I want to emphasize is that it's yet not the derivative itself, because it depends on this delta phi part, delta psi part. Okay, to make a derivative out of it, we need to consider this as an operator, essentially, or the functional of this. Okay? To make it I guess more specific. Let's just consider one case. One simple function now, not a tilde, but say the just psi square dx, right? So this is a function now, let's say s of psi. Okay. So then the derivative of Gateau differential will be equals to d over dt. And then what we need to differentiate is the integral psi plus delta psi times t squared dx. Right, and take t equals 0. So as I promised, although it's an integral of functions, but really this is just a function of t, right? And you can easily just go with your derivative inside the integral and differentiate. It's like differentiation of the integral that depends on the parameter, right? I don't know whether you've studied that, but if the parameter is inside, it's very easy. You just differentiate the integrand. It's a little bit trickier if the parameter is an integral, but still doable. Anyway, so when we do this, the normal rules of differentiation come into play, right? So we have 2, and then we have multiplied by the delta phi is a kind of a direction in which we vary. Okay, so we differentiated the square as a complex complex function, right? Where this is our variable. These are, for our differentiation purpose, they're just constants, right?
Yeah.
So that's why we get 2, the same expression, and then we differentiate this, we get the constant out, right? So then we take a limit that the t must be 0, right? And this is still inside the integral. So then if we take the t equals 0 limit, then this is gone, but this will stay, and psi will stay, right? And so this will be 2 integrals of psi multiplied by delta psi dx. Right? And so this construction can be thought then as an operator, which is 2 integral of psi of x. And then there is a placeholder here where you put whatever function you want. And in our case, this function is nabla, not nabla, but the delta psi, right? So if you give me a delta psi, then there is this operator that acts on it, and it's a linear operator, right? And then produces this result, which is a variation, okay? And so this operator is called derivative. No. Okay? Yeah.
Is it the weak derivative?
It's a weak derivative.
That's
yeah.
the weak, okay.
That's a weak derivative.
So the weak derivative is an integral.
It's a linear, it can be non-linear operator, but in this case, it is linear operator. And actually, when the Frechet and the Gateau derivatives are coinciding, then Frechet is always linear, but Gateau may be not linear. But in this case, it's linear. So it's a called weak derivative.
So we started off by saying the integral of a function's like psi squared, like right at the beginning over there. One step up, one line up.
Mm-hmm.
And is that squared or is that like
square?
Okay.
It's a square.
Okay.
I didn't want to deal with the conjugate right now.
Because otherwise it would be equal to 1, because our wave functions are going to be normalizable.
Or we'll get to the conjugation when we will differentiate this function, the e, because there is a conjugation. And there is a way to deal with the conjugation. The conjugation, though, may create issues. If you know complex calculus, function is analytical and differentiable only if it doesn't depend on the conjugation of the variable. Okay, but in this particular case, the conjugation will not be important. So, and I'll show you how do we get rid of a conjugation. Okay, so, all right. Now we're all equipped to go and, well, essentially find the extremum. So one way to find the extremum is you just say that this must be 0 for any variation delta psi. Okay. There is this so-called quantor in math which defines like any, right? So this is going to be a condition for the extremum, necessary condition, as in the normal like multivariable calculus, having all the derivatives to be 0 doesn't necessarily mean that you are in a minimum, right? Or, well, you are in extremum. In that sense, it's a condition for extremum. Okay? But what it says, if you think about it, if you think about this delta psi as a direction in this infinite dimensional space, that means no matter which direction you choose, the variation should be always 0. Yeah? So it's the same as if you go the simple two-dimensional case, right? So no matter what direction you choose, if you are in the maximum or minimum, then the derivative will be 0. Okay? Because no matter what direction you choose, again, the profile will be like a parabola, right? And if you're in the minimum, then you're in the minimum. The derivative will be 0. Okay. Good. So, good. Now let's see how this all is useful in proving that a variational approach is completely equivalent to solving Schrödinger equation, either time dependent or time independent. All right. And unfortunately, I don't know any book which would kind of have exposure of variational calculus, at least in some details. They usually either just jump in and introduce this weird delta psi thing and then kind of pretend that everything is obvious, right? So, and those are the quite respectable books of Messi, and who else does that? Landau does that, I think, and many other places. But if you stick just with this definition, then you will be fine. I promise you. Like, just the only thing you need to remember is this, right? So you take the functional, and I will illustrate how it works. Yeah.
So when you're learning classical mechanics, you start with Newton's second law, and then we go, okay, that's kind of complicated. A better way to do things is the Lagrange equivalence. We're doing like a quantum analog here, where they're like, okay, start off with the Schrödinger equation, but now there's a better way to do things. We're going to have this detail that, or is that not the case?
Okay, so with the classical mechanics, my understanding is there are different ways to approach it, right? Mm-hmm. And action is just one way, but historically there was this Newton laws, right? Yeah. There were Faraday laws in electrodynamics. Yes. Then later, people who likes abstraction or I don't know, likes to generalize things, they came and then decided, okay, let's just formulate one action one functional
Yeah.
that will rule them all, right? Like in that movie about the ring. So they cooked up the functional S, and and generated the rules how to create this functional, so that by varying the functional you can obtain classical Newton equations through Lagrangian formalism, or you can go and derive the Faraday equations if you set up the action properly. So it's all just nice, but whether it's a fundamental theory and there is nothing else, I wouldn't be so sure, because it's just one way to look at things, which is general and beautiful and all kind of.
And is that what we're doing here, but like quantum mechanically?
Yeah, you can think about quantum mechanical analysis, because the time-dependent Schrödinger equation, it's kind of just a postulate, right? So we didn't derive it from anywhere. So there is this equation. How do we solve it? One way, which is completely equivalent to solving it just directly as a differential equation, would be to reformulate it as a variational problem. And if you do variation in infinite dimensional space, what I will show you now is that it will be completely equivalent to solving the differential equation.
Okay.
If you're varying your functional in a finite space, then you'll get approximation. Okay, but you can then generate many approximations, and it's really easy. Like all you need is just to change the trial function, and then you obtain different equations.
Okay.
Right? And that's the idea. Okay, so here's the functional E. I switch from E tilde to E. I hope you don't mind. It's just don't want to write another tilde. Okay, so this is just psi h psi divided by psi, right? Now we do the variation, psi, and our variation will be 0. That's the condition for the extremum. And then this variation of E, that's what you usually would see in the text. Instead of writing this and emphasizing that it depends on the way you vary, they usually write in a short notation, like just delta E. Okay, and then this is the derivative with respect to t of E, where we have psi plus t nabla psi, and then we have limit 0. Okay, so then we need to differentiate with respect to t the following quantity: psi plus nabla psi t h psi plus nabla psi t divided by psi plus. Okay, straightforward so far, right? So okay, then this is a very simple differentiation, just lengthy, and yeah.
Would we just write it out in terms of integrals and then use the quotient rule?
Quotient rule.
Or
No, it's just,
whatever.
well, it's very simple, because essentially you have a function in the numerator that depends on t, and the function in the denominator that depends on t, right? So all you need is differentiate the ratio of two functions, and we know how to do it, right? So you first, one way is just first differentiate the numerator, and I will put the denominator as is, untouched. Plus, when we take t0, the denominator will be psi only. So it's very straightforward. And then in numerator, we differentiate with respect to t. What we'll get is nabla psi and h psi plus complex conjugate expression, where we do differentiation in the ket part.
Why does the first side? Oh, because the partial derivative.
Can you follow, or do I need to explain, because there are a couple of steps I kind of assumed obvious? Okay, because you essentially differentiate, you get rid of psi when you differentiate, and you also are losing t, so you're left with nabla, I keep saying nabla, delta psi, right? But in this part, you didn't differentiate, so you have t, but delta psi will be killed by this limit, and that's why it's psi. Okay, and in the second term, we differentiate in here, and we are removing the delta psi by taking the limit, right? And also, these guys are going to be destroyed by this limit as well, so that's why we're only left with psi's and denominators, right? Then there is a differentiation of denominator, and then you can, I will continue here, what you will have -1, because it's a minus first power, you can think of, and then you have psi, h psi, divided by psi squared. Okay, and then there will be this and term this. Okay, so the same technique, you differentiate this as a complex function, and then you different complex means in terms of the function inside of the function, not with a complex variable. Okay, so then you take in the t equals 0 limit, and that's what you get. Now, it is helpful to recognize that actually psi h psi divided by psi is just e, right? So what we get out of this term is minus e, our functional back, and then multiplied by, divided by psi, and then multiplied by nabla, delta psi plus psi, right? And then this part plus this part, they're supposed to be together. They're supposed to give you 0, right? Oh, that was our condition of extremum, right? So we differentiated, and we obtain these two pieces, and together they should give you 0. What does that mean? That means that together they are 0. That we can simply remove the psi part out of the denominator, and what we will be left with, let me continue here, a relatively simple expression which is yeah, that's right. So whatever is here is essentially this. Okay.
And does that equal, like, adding those terms together, or?
Okay, so and then
that equals that.
okay, so then this part is continued here, right? So only this part. All right, only this part.
Where does the next equal sign begin? So you have equals this, and then equals the thing on top, and then equals the thing in the middle?
Yeah, let me write down the whole thing so that it won't be. Or can we actually move? Can we move this? All right.
Bottom equals 0?
That's it. And then he said the top simplifies the middle. So
Okay, so let.
top is 0 or top is 0.
So this is with minus. Then you have psi h psi. Oh, if you do the algebra at home, then you can just repeat this. Yeah, this is the least favorite part of mine, doing the variational approach, differentiation. ratios. And so we have psi. Okay? And this must be 0, this whole thing together. Okay? Because it is 0 because to find an extremum, we have this condition, right? And all we did so far is just obtain the delta E, which is this expression, right? And so then we noted that this guy is just E, right? And then we can, since whole thing is 0 and the denominator is something finite, then we just remove the denominator from our consideration to make things simpler. And then what we get is, we can also put the E constant inside. And we have these two very simple expressions, which together should start to remind you time-independent Schrödinger equation. It's just in a slightly weird form. But first weird part about this expression is, well, there are two components, right? And if some of them is 0, that means either both of them are 0, or they are just one is equal to another with a minus sign, right? And so now I can show you that actually the second choice, that this is equal to minus psi h minus e, is not right. How do I show you this? And I'm kind of alluding towards the fact that these both should be 0 independently. But why we cannot have this term be equal to this term with a minus sign? As I said in the beginning, this extremum condition, this variation must be 0 for any nabla delta psi. And if it is true for this kind of reduction to absurdum way of showing this, and so if this is true, say, imagine this is true, right? If it's true for this delta psi, then it should be also true for I delta psi, which is just the same variation but multiplied by I, the complex unit, right? And so these two are different in the way we treat, where we put the variation of psi. So here it's an ket vector, and I would just go outside. So minus, we write this expression now, h minus e, nabla psi. And if we have I here, we can put it in front of the expression. And this must be equal to the upper expression with I now. But since I in the bra, we can put it outside with minus I, right? And so now we can remove i's with minuses. And what did we get? We actually got that the psi h e minus e nabla delta psi is equal to delta psi h minus e psi. So we started with this assumption, but then we arrived to assumption which is contradicting with our initial assumption. Okay, so that's why this cannot be true, and both terms must be equal to 0 independently. Okay. Now, if both terms equal to 0 independently, then we can work with any of this. And since delta psi is completely arbitrary, for, say, delta psi h minus e psi to be 0, what we need is h minus e psi to be 0 identically, right? Not in 1 or 2 points, but everywhere. because this delta psi can be any function, right? So, and this is an integral of any function with some function. And so if any function with some function integrated should be giving you 0, then it means that you're integrating this some function with 0. That's the only way. And then this is just a Schrödinger equation in a different form, right? So this shows that if you do complete variation in an infinite dimensional space, then starting with the variation condition, you obtain time-independent Schrödinger equation. Okay?
So going back quite a bit, we have that derivative there, like the taking delta of our functional instead of being equal to 0.
Mm-hmm.
And that derivative is the derivative that we have defined over there that takes with the value of t equals 0. Is that also a weak derivative, or does that have a name?
The derivative I specified here, right?
No, one step. And that was a weak derivative, yeah. But the one step up.
This is a variation. This is differential, right?
So this is a differential of functional.
Right.
And is a differential always going to be take the derivative and evaluate it at 0?
Differential is essentially, I guess, a map between two objects, the psi and the delta psi, into the domain of numbers, right?
Yes.
And then if we decide to formulate a derivative, we're taking this delta psi outside, and then the derivative becomes our operator, right? Or, I guess, functional of one function, delta psi, that gives you a number, right?
I'm just confused how we got to that functional. The derivative was at the time, which I would expect, but then evaluated at t equals 0, which I wouldn't expect. Like, why do we do that?
For the same reason, well, okay, it's a valid question. It's very important to understand. We're going back to the directional derivative, right? When we set up direction, it's a finite vector. It's a vector of the length of 1, right?
Yes.
And in order to go to the calculus is all about changing in a very infinitesimally small distances, right?
Yeah.
But if the direction is not infinitesimally small, then you need to have a small parameter,
Okay.
right? And so that is why we have a transfer to,
That's why we evaluated at t equals 0.
yeah.
It's like when h goes to 0 when you do normal derivative.
Okay.
Yeah,
So it's sort of like a limit.
that's right.
Okay. Okay.
You can write it as a limit as well. Yeah. Okay. All right. Now, turns out that this can be generalized to time-dependent with time-dependent Schrödinger equation. And
Go over again what you do with the I.
okay, with the I, yeah, I thought it was maybe a bit confusing. So the whole I consideration started from possible doubts. If we have this expression, right, where we have two terms, and together they give you 0. There are two choices now, or two possibilities, really. It's either each of them is 0, or one cancels another, okay? And to avoid the second possibility, I considered the situation where I changed the delta psi to I delta psi, okay? That was a construction that reduced to absurdum this assumption essentially, that this guy is just a minus that guy, right? So if we start with this assumption, then this should be true for any delta psi, not for some particular delta psi, right? Because we're looking for extremum where no matter what delta psi we put, this condition is true. Then we substitute with I delta psi and saw that actually the sign will flip. Okay, and then we concluded that actually now each term must be 0. Okay. All right, so let me just finish on the time-dependent Schrödinger equation, where everything can be repeated just with different functional. And the functional can be, there are two actually time-dependent variational principles. They call time-dependent variational principles. And Tanner has a chapter on that. One principle is so-called Dirac-Frankel principle. There, the functional is, say, equals to psi h minus I d over dt psi. Okay. There is no denominator because what we usually have is the unitary propagation in the time-dependent Schrödinger equation, and that's why the norm of psi stays constant, right? So that's why we have just this functional, and if we vary j psi j, right? Essentially, the only difference is now instead of e, like in the previous form, we would have this time derivative, right? And the same consideration will be applicable, and if we require that this is 0, then the alternative kind of condition will be h minus I d over dt acting on psi is equal to 0. So this is derivable exactly the same way. It's just there is no denominator, so it will be much easier to differentiate the whole thing. The logic about the fact that both terms with delta psi in the Brouwer ket should be 0 stays the same, and then you obtain this equation, which is time-dependent Schrödinger equation. Alternatively, there is another flavor which Tanner prefers. Kind of makes it whole thing kind of easier to understand, I believe, in case when the wave function is parameterized with a finite number of parameters, so-called McLaughlin principle. And there we assume that, okay, so we have some parameterization of psi, and our IH d psi dt is equal to theta of t. And then, if we have finite parameterization of psi, then our theta t is not equal to h psi, right? So h psi, no matter what parameterization you take for psi, h is an operator, say, in a space, right? So then it will produce something that is exact. And if your function depends on parameters, and through those parameters you have time dependence, then the derivative with respect to time is not going to be exact derivative. So those two terms will not be exactly the same in the approximate representation of psi. So McLaughlin principle will minimize the following functional then. The functional g prime with respect to theta will be h psi minus theta t, h psi minus theta t. Okay, and then we do the same kind of approach. G prime, variation, theta, delta theta, which will give us plus complex conjugated part. This all 0, and then this is equivalent to h psi equals to theta or I d psi dt with h bar. Okay, so these two principles, they are equivalent, or the equations you arrive with those two principles, they are equivalent for most of the problems. So they sometimes mention like Dirac-Frankel McLaughlin principle for solving time-dependent Schrödinger equation, but they're slightly different in formulation. Okay, so I guess we're running out of time, and next lecture I will start with application of this to particular constructions for the trial wave function, linear and nonlinear. Now,
Does this course have a midterm?
sorry?
I can't remember if this course has a midterm.
I need to check myself. I teach 2 courses, so
Our course is not.
yes, graduate
Our course has a final midterm.
Yeah.
graduate
No
doesn't have.
final or midterm?
No,
You have a final
we think
midterm.
you do.
Oh, I have a final, you have a presentation.
Yeah.
That's right.
But I think you also have a midterm.
Oh,
But like, you can always have a take-home midterm assignment sort of thing, which can just be our midterm / take-home assignment.
Yeah, we'll figure something out. I'll let you know. I just don't remember. I think C21 definitely, another course I teach, definitely has a midterm. Whether I cancel midterm for this one, and I also know that definitely you have finals, because it will be hard to cancel those.
yeah.
But whether you have midterm or not, we can do take home probably as a
So
kind
take
of
over
for you, and
assignment,
then
yeah.
homework for them.
Your take-home midterm is our assignment.
Yeah, it's a good
Okay.
idea.